Hi children, welcome. Welcome to another chemistry class. In this class, we are going to review the chapter Electrochemistry, one of the most important chapter from the 12th standard topic, Electrochemistry, chapter 3. Okay, can we start? Ready? Yes. See, the basic content of the chapter Electrochemistry comes as a continuation of redox reaction that we learned in the 11th standard topic, all of you know, right? Electrochemistry dealing with the conversion of chemical energy. Chemical energy is converted to electrical energy and vice versa. Electrical energy converted to chemical energy. So chemical energy stored in a system converted to electrical energy and electrical energy converted to chemical energy. Together we call it as electrochemical reactions. Electrochemical reactions, right? And a device used for converting chemical energy into electrical energy, all of you know it is called a galvanic cell. It's a typical electrochemical cell. Electrochemical cell. A typical example is galvanic cell. Galvanic cell or Daniel cell. It is a naturally working system. It is a spontaneous process involved where chemical energy is converted to electrical energy. Okay, the reaction is spontaneous in nature. The reaction is spontaneous in nature where delta G is negative and EMF is positive. All of you know delta G is equal to minus NFE. So this is positive, quite naturally delta G is negative. This is what the reaction happening in galvanic cell where it is a device where chemical energy is converted to electrical energy. A typical example is zinc copper couple where the reverse reaction, electrical energy converted to chemical energy, extraction of various metals, electroplating, etc. fall under that category. We call it as electrolytic cells. Electrolytic cells. And that is a non-spontaneous process. Non-spontaneous process where delta G is positive and EMF is negative. EMF negative means we are giving energy to the system. We are supplying energy to the system and thereby we proceed extraction of some metals, thereby we proceed preparation of some monic compounds, thereby we proceed some electroplating processes, etc. In the other case, chemical energy stored is released as electrical energy. That is a spontaneous process. EMF positive, delta G negative. This is non-spontaneous process. EMF negative, delta G positive. A typical example is for the device for chemical energy to electrical energy. It is a galvanic cell. Galvanic cell. All of you know how the galvanic cell functioning is explained. For example, a zinc copper couple. A zinc copper couple, which is a typical example for a galvanic cell, which is a vessel taken where zinc sulfate solution is taken and a zinc rod is immersed into the system. And we have another vessel which is taken with a copper sulfate solution is taken and a copper rod is immersed into it. And they are connected externally. They are connected externally, and this I am keeping a voltmeter. This connection is called this is functioning as a natural cell where chemical energy stored in the system, the potential stored in the system, copper, zinc, metals is converted to electrical energy. And there is a device all of you know or remember definitely. This is called a salt bridge. A salt bridge, the mouth of which is closed using cotton plug and it is filled with some neutral electrolyte like say KCl, KNO3, some ammonium chloride, etc. Some neutral electrolytes are filled with some jelly material filled inside, and the mouth are blocked using some cotton plug and is connecting the two solutions, which is called a salt bridge. This is a salt bridge. A salt bridge is permitting the flow of charges from one position to one solution to another, thereby maintaining internal electrical circuit completion. All of you know this works as anode. This works as anode, a negative terminal, and where there is oxidation is taking place. Zinc is dissolving into the solution as zinc 2 plus, and the released electrons are traveling through the external circuit and reaches the cathode, which is a positive plate, and that is a cathode where reduction is taking place. So here zinc is dissolving in the solution, that is zinc solid is converted to Zn2 plus aqueous plus 2 electron, that is oxidation. Now that electron reaches here, there is reduction. Cu2 plus from the solution absorb 2 electron and is converted to Cu solid. Cu2 plus from the solution is deposited on the electrode using the electrons that is coming. So on the course of time, I don't have to tell you, all of you know, on the course of time, there will be a decay in the anode. See, this is dissolving. Zinc is dissolving. On the course of time, the zinc anode will undergo a decay, whereas there will be a growth in the copper cathode. And this is maintaining an imbalance of charge in the two solutions. Here there will be a accumulation of positive charge because zinc is dissolving. Here there will be a deficiency of positive charge because Cu2 plus is depositing on the metal surface. So there will be a charge imbalancing which is maintained by salt bridge. Salt bridge is providing the migration of ions from one solution to another, thereby providing the charge in balancing, the potential difference is maintained. It is completing the internal circuit completion. If there is no salt bridge used, of course the system will work initially, but after some time it will stop because it cannot sustain the reaction. This is what a galvanic cell, this is what a typical example of a galvanic cell, right, which is maintaining with a potential difference E naught value, E naught cell is equal to E naught cathode minus E naught anode. Here cathode is copper whose value is 0.34 volt and anode is minus 0.76 volt, that is zinc. The standard reduction potential that is tabulated in electrochemical series, the application of electrochemical series we will discuss in detail after some time. So the electrode potential of cathode, that is copper, plus 0.34 and that of anode minus 0.76, you will get 1.1 volt. That is the standard EMF of the cell that we are using. Hope you know standard EMF means 1 molar concentration of electrolyte at a standard temperature 298 Kelvin. That is called a standard condition, and the EMF at that point is standard EMF. So the EMF of the cell is 1.1 volt. Now there is an experiment explained in the NCERT. You might have seen that the figure diagram 3.2 ABC, 3.2 ABC. For example, the first diagram you see, the one where you see the standard EMF of the cell is 1.1 volt. This is a zinc copper couple, the one which I have explained now, having a potential of 1.1 volt. Now we are applying an external source. This is an external source connected to the cell given. You can see the external EMF given less than 1.1 volt. That means the cell output is 1.1 volt. Understand clearly, cell output is 1.1 volt. You are giving an opposite EMF less than 1.1 volt. For example, say 0.5 volt you are giving from the external source. So the cell is connected to external source. The cell is providing an EMF 1.1 volt. External source opposing energy we are giving 0.5 volt. What will happen? You just tell me. What is going to happen? In which direction there will be net potential, net EMF? Very simple. Very simple. It will be net will be from away from the cell out of from the cell out. So it will be 1.1, 0.5. It will be 0.6 volt provided by the cell. That means everything will work as we have explained. At anode there will be oxidation. At a cathode there will be reduction. There will be flow of electron from anode to cathode, and the conventional flow of electricity will be in the opposite direction. Everything happens the way we have discussed. Now, suppose we go to the diagram third one. The diagram third one, you can see the external EMF is greater than 1.1 volt. That means the cell is providing a voltage 1.1 volt. We are giving a voltage say 2.5 volt. So external source is giving a potential greater than the EMF of the cell. What will happen? Everything will reverse. Everything will reverse, because now the net EMF is in this direction. It is 1.1 and 2.5. How much it is? 1.1, 2.5. How much it is? 1.4, right? So it will be 1.4 volt in this direction. That means the cell is getting energy. That means it will work as an electrolytic cell. Everything will reverse. Everything will reverse. Now this is acting as a cathode. This is acting as an anode. There will be oxidation here. There will be reduction here. Flow of electrons will be from this to this, and conventional flow of current will be from this to this. Everything reverses. Now it acts as an electrolytic cell. Just opposite. Because now the energy is given to the system. Now what if the external EMF and the cell EMF are equal? The cell EMF is 1.1 volt and the external EMF is 1.1 volt. Nothing is going to happen. No net EMF, no net reaction. We can say it is under equilibrium. No flow of electrons, no current flow, no reaction, no net reaction. Is it clear? Is it clear? That is what the three experimental situation explained in the text. Okay. Now into the details of cell representation and the cell reaction. Into the details of cell representation and cell reaction. A cell can be written like this. The previous reaction, zinc solid plus copper sulfate aqueous giving Cu solid plus zinc sulfate aqueous. This is zinc copper coupled reaction, right? So it's simple to understand. Zinc is undergoing oxidation. Zinc is undergoing oxidation while copper is undergoing reduction, and that way the cell is represented. Cell is represented as zinc solid converted to zinc 2 plus aqueous, and the concentration will be written X molar. This is anode reaction. Zinc is oxidized to zinc 2 plus. Now we put a double slash representing salt bridge, and then it is Cu2 plus aqueous, say Y molar slash Cu solid, that is cathode half cell, that is reduction reaction. So this way we represent a normal galvanic cell, right? You see, zinc is oxidized to zinc 2 plus anode reaction, Cu2 plus is reduced to Cu cathode reaction and is separated by salt bridge. Is it clear? Is it clear? Right. Suppose we are writing a reaction like this. For example, suppose we are writing a reaction. See, platinum H2 2 bar slash H plus 0.1 molar double slash Cu2 plus 0.1 molar slash Cu solid. You see, this is a cell representation. This is a cell reaction where we can see there is a gaseous matter involved. Quite naturally, there will be a solid inert electrode which will be incorporated, because gaseous matter with the help of a solid electrode, it cannot take part in the reaction. That way it is written. And how to represent the cell reaction? Cell reaction is quite simple. It is H2 converted to 2H plus and Cu2 plus converted to Cu. This is the cell reaction. This is the cell reaction. So writing the cell representation and writing the cell reaction, it is very important to understand. Okay. Similarly, regarding standard reduction potential, all of you know the reduction potentials are tabulated using a reference electrode which is called SHE. SHE. We have a reference electrode for finding the standard reduction potential. This is SHE, standard hydrogen electrode, known to all. Standard hydrogen electrode. Standard hydrogen electrode means you have such a system, you have a platinum wire and finely divided platinum coated on platinum foil. Finely divided platinum coated on platinum foil, like that. We are taking a concentration 1 molar acid solution and we are pumping hydrogen gas at 1 bar. So hydrogen gas pumped at 1 bar, which is bubbling out through the system, will take part in the chemical reaction. And this is standard hydrogen electrode whose potential is fixed as 0. Whose potential is fixed as 0. So this potential, standard hydrogen electrode potential, is arbitrarily fixed as 0. So E naught value H plus bar H2, it is arbitrarily fixed as 0 volt. Using this, we find the standard reduction potential of various substances. For example, how do we find the standard potential of copper? It is with this reaction. This will work as SHE. This will work as SHE. Rather, instead of 2 bar, it must be 1 bar pressure and the concentration should be 1 molar to get standard condition. So I am taking 1 bar hydrogen pressure, 1 molar concentration, 1 molar concentration. Now this electrode is nothing but SHE. This is SHE which work as anode. Why this is working as anode? Because copper is less reactive, we know, and this will work as cathode. This will work as cathode. So we construct such a cell. We construct such a cell taking anode SHE. SHE act as anode. SHE act as anode and copper electrode act as cathode, and we connect it externally. We find the potential. Experimentally, you can get the potential under standard condition. You get 0.34 volt. You will get it as 0.34 volt. That means you are able to write E naught cell is equal to E naught cathode minus E naught anode. Now that is 0.34 is equal to E naught cathode. Cathode is copper and hydrogen is anode. So copper value E naught Cu2 plus bar Cu minus E naught H plus bar H2. And the value for this is arbitrarily fixed as 0. So it is 0.34 is equal to E naught Cu2 plus bar Cu minus 0. That means E0 Cu2 plus bar Cu, you will get 0.34 volt, which is positive. That is the way you get the value standard reduction potential of a particular species by coupling with the SHE. And SHE we have arbitrarily fixed as 0. Is it clear? Suppose at the same time we are taking zinc. What is the scenario? Suppose it is zinc versus SHE. Please understand, zinc will act as anode. Zinc electrode will act as anode because it is more reactive, and SHE will act as cathode. So when you compare This is working as anode, and when you connect it externally, connecting with a voltmeter, the potential difference that you're going to get is 0.76 volt under standard condition. Under standard condition, you will get a voltage 0.76 volt. Now once again, what is the calculation? E naught cell is equal to E naught cathode minus E naught anode. That is 0.76 is equal to, here cathode is SHE. SHE value is 0 minus E naught zinc 2 plus bar zinc. So what is the E naught value for zinc 2 plus bar zinc? E naught value for zinc 2 plus bar zinc, it is minus 0.76 volt as is tabulated in electrochemical series. This is how the values of various species are tabulated in electrochemical series. It is actually by coupling with SHE. So by coupling with SHE, if you prepare such a cell under standard condition, definitely you can experience, you will get a voltage 0.76 volt, and that voltage we assign to zinc with a negative sign according to the formula. Here the voltage assigned to copper with a positive sign according to the formula. Is it clear? Is it clear? And based on which various species are enlisted in electrochemical series as a reference of hydrogen. As a reference to hydrogen, and this is the electrochemical series. This is the electrochemical series known to all. This is the electrochemical series where you can find the reference material is hydrogen having 0. Active metals are available below hydrogen having negative reduction potential. They have a negative reduction potential, while less active metals are available on top of hydrogen, and even non-metals are available on top of hydrogen. You can see increasing strength of oxidizing agent, increasing strength of reducing agent. So this is the powerful oxidizing agent, and this is the powerful reducing agent. So as you move from bottom to top, the reducing power increases. Fluorine most powerful, then cobalt, H2O2, like that. Chlorine second place, bromine third place, iodine last. That is the way halogens are coming, their oxidizing power. Fluorine most powerful oxidizing agent because it has got a high reduction potential. F2 has got a high tendency to undergo reduction. It has got a high reduction potential. That means it undergo easy reduction. That means it is a very good oxidizing agent. Meanwhile, lithium plus cannot undergo easy reduction as the potential is negative. It has got a negative reduction potential. What does that mean? The point is lithium will be easily oxidized to lithium plus. So a negative reduction potential means this is oxidized to this. That means this acts as a strong reducing agent. So let me make a conclusion. The point is very simple to understand. See, E naught value F2 bar F minus, which is a very high positive figure, 2 point, how much was the value? 2.87 plus 2.87 volt, high positive figure. That means this is easily reduced to this, and this is a strong oxidizing agent. This is a weak reducing agent. That is the point. Keep it in mind clearly. A high reduction potential means this is easily reduced to this, and this is a powerful oxidizing agent, and this is a weak reducing agent. You can consider any species. You can consider any species E naught X bar Y, high positive figure. What is the meaning? The meaning is X is converted to Y. X is reduced to Y easily, and X is a strong oxidizing agent, and Y is a weak reducing agent. That is the meaning. Is that okay? Now, in contrary, suppose you have E0 value Li plus bar Li, which is high negative, 3 minus 3.5 volt, high negative. What does that mean? This means that lithium is easily oxidized to lithium plus. Just opposite. Just opposite. Lithium is easily oxidized to lithium plus. That means this is a strong reducing agent and this is a weak oxidizing agent. Now upon generalizing, suppose you have E naught A bar B having high negative figure. What does that mean? What does that mean? This means B is easily oxidized to A and B is a strong reducing agent and A is a weak oxidizing agent. That is the meaning. So this can give you a relative comparison of the nature of the species. Say for example, this you need to be paka clear on your mind. Suppose you are given with such a question, E naught value A bar B given as plus 1.87, C bar D given as minus 2.31, E bar F given as minus 0.76. Now G bar H given as plus 2.81. Now X bar Y given as minus 1.36 and P bar Q given as plus 0.8. This way the potentials are given. Just imagine. And the question comes arranged in the increasing order of oxidizing agent. What is the increasing strength of oxidizing agent? How do you do? Oxidizing agent. Oxidizing agent if you are trying. Oxidizing agent if you are working out. Look at the high positive value. High positive value this one and select the one species on left hand side. So G is powerful oxidizing agent. Now who is next? Next high positive here. So it is A next. Who is next? Next high positive. It is P. Then who is coming? Then who is coming? After this it is E. E and last will be C. This is the order of oxidizing agent strength. G is in the list. G is powerful oxidizing agent and C is weak oxidizing agent. Now the next question. What is the order of reducing strength? Order of reducing agent strength. How it comes? Then you will go for high negative. Just opposite. Just opposite. High negative first. And you will select the species on right hand side. So D will be maximum. D will be maximum. After D it will be Y. Then who is coming after D, Y, then it will be minus F. It is minus F. Then after F it will be Q. It will be Q. And after Q it is going to be which one? After Q it will be B. And after B only it will be H. This is the order. This is the order of reducing strength. The most powerful reducing agent is D and least powerful is H. Now, from the list, G can oxidize everybody. G can oxidize all. Similarly, D can reduce all. That way, we need to understand the content. Right? We need to practice as much as possible. We are going to practice through the questions also. So the powerful oxidizing agent will be this one in the list and powerful reducing agent will be this one. This can reduce all in the list and this can oxidize all in the list. This can oxidize all here. All this will be oxidized by this and all this will be reduced by this. That is the point. Now randomly if you pick two species, for example, I am picking zinc and copper, I am picking zinc and copper. I don't have to tell you, the one below will act as anode, one above will act as cathode. Randomly if you pick two species, the one below will act as anode, one above will act as cathode. That is what the scenario, that is what the kind of application related to electrochemical series. Is it clear? Fine. Next is writing Nernst equation. Next is writing Nernst equation. Nernst equation for electrochemical cells. Nernst equation. Nernst equation is actually talking about EMF versus concentration. That is what Nernst equation. Nernst equation is talking about potential versus concentration. That is the prime point of concept link between, used in Nernst equation. How the Nernst equation can be understood? Suppose we take an electrode reaction, Mn plus n electron giving M. Suppose we take such an electrode reaction. Always the electrode reactions are represented in reduction type reaction. So the way we have represented an electrode reaction. Okay, how way you write the Nernst equation? Nernst equation will be E Mn plus bar M is equal to E naught Mn plus bar M. This is the data available in the table. Minus 2.303 RT by NF log 1 by concentration of Mn plus. Actually, this term will come in the numerator, but the concentration of solids are taken as unity. Concentration of solids are taken as unity. Therefore, it is omitted. Okay. So, this is the basic Nernst equation for a particular electrode reaction. Right? And this much data you can consider applying or simplifying this much data, 2.303 RT by F. You can simplify and you can write 0.0591. This can be written as 0.0591 by substituting the standard constant values. Okay. So suppose we are writing the reaction Zn2 plus 2 electron giving Zn. The equation will be E Zn2 plus bar Zn equal to E naught Zn2 plus bar Zn minus 0.0591 by 2 log 1 by Zn2 plus concentration. This will be the Nernst equation written for zinc zinc electrode. What about copper electrode? Cu2 plus 2 electron giving Cu. How do we write the Nernst equation? E Cu2 plus bar Cu equal to E naught Cu2 plus bar Cu minus 0.0591 by 2 log 1 by Cu2 plus concentration comes like this. Right? Now applying both together, you can find the Nernst equation for the cell reaction. How do we get the cell reaction? How do we get the Nernst equation for cell? We know E cell is equal to E cathode minus E anode. E cell is equal to E cathode minus E anode. And this is cathode, and this is anode. So equation 1, equation 2. 2 minus 1 will give you this. So the result is going to be equation 2 minus equation 1. This equation minus this equation, that will take you ultimately this value minus this value. It will be E cell, that is equal to this value minus this value, that will be E naught to cell minus 0.0591 0.0591 by 2 log this value minus this value will take you to zinc 2 plus concentration in the numerator and Cu2 plus concentration in the denominator. This is the way the Nernst equation comes for zinc copper couple. Right? I'm just reminding all these points. Now for a general reaction considering the normal hypothetical equation, A moles of A plus, B moles of B giving C moles of C plus, D moles of D. How do we write? It will be E cell is equal to E naught cell minus 0.0591 by N log product by reactant. It will be log product by reactant. You see what is a reaction here? It is Zn solid plus Cu2 plus aqueous giving Cu solid plus Zn2 plus aqueous. You see product by reactant. Why these two terms are not in the Nernst equation? A solid matter will not appear in the Nernst equation. A solid matter will not appear in the Nernst equation. It is only gaseous aqueous solutions are coming. Their concentration will come in gaseous matter. Partial pressure will appear in Nernst equation. Okay. Now, it is product side zinc by reactant side Cu2 plus. Like that you can apply here. Product by reactant, it will be C raised to C into D raised to D divided by A raised to A into B raised to B. Like that. Like that. Is it clear? Is it clear? Now this formula I can tell you the concept of equilibrium, which is E cell is equal to E naught cell minus 0.0591 by N log QC. This is nothing but QC. Reaction quotient. Hope you remember. Reaction quotient. Right? Now, at equilibrium, E cell is equal to 0. At equilibrium, EMF of the cell will be 0 because no net EMF. So what do you get? Upon simplification, what do you get? At equilibrium, E cell is equal to 0. Also QC equal to KC. Now you will get the relation 0 equal to E0 cell minus 0.0591 by N log Kc. Right? That takes you to the relation E naught cell is equal to 0.0591 by N log Kc. Or applying the entire format, it will be E naught cell is equal to 2.303 RT by NF log Kc. Right? Or it is NF E naught cell is equal to 2.303 RT log Kc. Now you know this how related to delta G. Delta G is equal to minus delta G naught is equal to minus NF E naught cell. So this you can correlate there. How do you get? Delta G naught is equal to minus 2.303 RT log Kc. Already this we have learned in the chapter equilibrium, thermodynamics, etc. All this you can correlate and try to remember the various different formulae connecting and equip yourself practicing the numericals concerned on this. How to get the further relation, I'm just reminding you how you can proceed. You see log Kc is equal to delta G naught by 2.303 RT. Therefore, Kc is equal to 10 to the power minus delta G naught by 2.303 RT, like this. or even it can be ln Kc. Ln Kc is equal to minus delta G naught by RT. Therefore, Kc is equal to e to the power delta G naught by RT, like this. We don't know exactly what kind of formula we are about to encounter in a particular numerical. We don't know. All types variations you can practice, you can think about your own, the various way of manipulating a given formula. Right? So all these are has to be taken care of, which is related to Nernst equation, right? Now our next topic is on various terminology, like what is resistance. We need to go through resistance R, conductance kappa, cell constant, etc. Resistance, conductance G, resistance, conductance G, resistivity rho, conductivity kappa, molar conductance, various such terminologies we need to discuss, right? So the term resistance, number one, I don't have to tell you the term resistance coming from Ohm's law. Term resistance is coming from Ohm's law. All of you know Ohm's law, V is equal to IR, and that is introducing the term resistance, which is opposition to the flow of electricity, right? All of you are aware, resistance of a conductor is directly proportional to length of the conductor and inversely proportional to area of cross section. Resistance offered by a conductor, it is directly proportional to length of the conductor and inversely proportional to area of cross section, right? And R is equal to a constant rho into L by A, where rho is called a specific resistance. Specific resistance called resistivity. Specific resistance called resistivity. How do you define resistivity? Resistivity is defined as R is equal to rho when L equal to 1, A equal to 1. So rho resistivity is defined as resistance offered by, rho is the resistance offered by a conductor of unit length and unit area of cross section, or in case of electrolytes, unit volume. Okay. And moreover, rho is equal to R into A by L. The unit of R is ohms and centimeter square by centimeter. So it is ohms centimeter in CGS system or ohm meter in SI system. That is a unit of the specific resistance, the so-called resistivity. Resistivity is nothing but the resistance offered by, resistivity is the resistance offered by a conductor having unit length and unit area of cross section, right? Now on to the term conductance. Conductance means the opposite of resistance, that is conductance. What is conductance? Conductance represented by G. In physics you will be dealing with the C term. No problem, the term changes no matter at all, concept remains the same. The conductance represented here in our NCERT textbook G. G is equal to 1 by R. So G is equal to 1 by rho into A by L. Already we have seen R is equal to rho into L by A. So 1 by R will be 1 by rho into A by L, right? And we can have G is equal to 1 by R is equal to 1 by rho is another term, kappa into A by L, where kappa, this is called kappa, that is specific conductance. Specific conductance. What is specific conductance? Specific conductance kappa is equal to G when L equal to 1, A equal to 1. So specific conductance, that is conductivity, specific conductance also called conductivity. Conductivity is defined as the conductance offered by a conductor of unit length and unit area of cross section, or in case of electrolytes, unit volume. So it is the conductance offered by unit volume solution, that is kappa, conductivity or specific conductance. Is it clear? Now here you can have a relation, kappa is equal to L by A divided by R, and this L by A is represented as G star. So you can write kappa is equal to G star divided by R. What is this G star? G star is nothing but L by A, the so-called cell constant. G star is nothing but L by A, and it is called a cell constant. Every conductivity cell that we use in the experimental systems in the laboratory will have a cell constant L by A, designated in our textbook as G star. So kappa conductivity is equal to G star by resistance. If you know resistance, you get kappa, provided the cell constant is available. How to find the resistance? Resistance is determined by Wheatstone-Bridge experiment. Hope you remember. You learned in the physics classes. Hopefully you are done in the practical lab also, physics laboratory. Wheatstone-Bridge experiment, potentiometer experiment, meter bridge experiment, post office box. At least Wheatstone-Bridge experiment, definitely you might have done in the laboratory. Using Wheatstone-Bridge experiment, you can find the resistance of unknown solution. How do you find the resistance of unknown solution? It is applying the Wheatstone-Bridge experiment. What is Wheatstone-Bridge experiment? We have a non-resistor R1. We have a non-resistor R1, and we have a variable resistor here, and we have the resistance which we need to find out. That is the conductivity cell we apply here. This is a conductivity cell where we have taken a solution whose resistance we want to find out. So let this be R1, let this be R2, which we need to find out. And here we have another non-resistance. This is a non-resistance. Say this is R3 and this is R4, right? And this is connected using a galvanometer like this. This is connected using a galvanometer. R1 is a fixed resistor. R2, this is R2, the resistance we need to find out. This is actually we need to find out the resistance of a solution taken in a conductivity cell. This is a typical conductivity cell which we can use in the laboratory. There is a horizontal and a vertical conductivity cell. This is a conductivity cell horizontal type. This is a vertical type conductivity cell. It will have a constant called a cell constant, L by A, length by area. Right? So that value will be fixed available. Once you know the resistance, you can kind of find out the kappa value. So we take such a system. This is a non-resistor. This is the resistance we want to find out. This is another non-resistor, and this is a variable resistor like a rheostat. Like a rheostat, a variable resistor available, and it is connected like this. I hope all of you know. It's connected like this. Now applying electricity, applying current through the system, there will be a deflection in the galvanometer. Now you can apply the resistance over this variable resistor by constantly changing. By small changes applied over the variable resistor, you can put the galvanometer in null deflection. Once you get the galvanometer in null deflection, you get the relation. And sure you remember R1 by R2. R1 by R2 is equal to R3 by R4. This value we know. This value we know. And this value we can find out the variable resistance offered by the rheostat by counting the number of coils that have been moved by moving that movable arrangement. We can find the resistance offered by the rheostat, which is a variable resistance. right? And R4 we know, and we need to find out R2, which we can calculate from the formula. R1 by R2 is equal to R3 by R4. We get the unknown resistance offered by that solution, which is used in the experimental system. Once you get resistance, you can, if you know the cell constant used by the conductivity cell, you can find out kappa. What is kappa? Kappa is the conductance offered by a solution of unit volume, while the total conductance offered is called molar conductance, lambda m. Molar conductance, it is kappa into V. That is the total conductance offered, molar conductance. Lambda m, molar conductance, total conductance offered by a solution having 1 molar concentration of electrolyte, 1 mole of electrolyte dissolved in a solution such that the electrodes are kept at unit centimeter distance. Lambda m. Lambda m can be calculated once you know kappa, once you know the concentration. If you know the concentration and the kappa value, you can find out lambda. Lambda m is equal to kappa into 1000 by molarity. Lambda m is equal to kappa into 1000 by molarity. I don't have to tell you the unit of kappa. Kappa is 1 by rho. Kappa is 1 by rho. You know the unit of rho. Unit of rho is ohm centimeter. Unit of rho is ohm centimeter. Therefore, unit of kappa is per ohm per centimeter, or it is per ohm per meter. It is called a Siemens meter inverse. Per ohm is called a Siemens. Per ohm is called a Siemens. Now the unit of lambda will be Siemens centimeter square per mole. Siemens centimeter square per mole. That is the unit of kappa. Or it can be Siemens meter square per mole. That is the unit of lambda m. Lambda m, the so-called molar conductance. Siemens centimeter square per mole, or Siemens meter square per mole. That is the unit lambda m, right? Also try to review the conversions of these two units. It is there in the NCERT. 1 Siemens centimeter square per mole is equal to 10 raised to minus 4 Siemens meter square per mole. As all of you know, 1 centimeter is equal to 10 power minus 2 meters. 1 centimeter is equal to 10 raised to minus 2 meters. Square will be 10 raised to minus 4. Similarly, 1 Siemens meter square per mole, very simple, it will be 10 raised to 4 Siemens centimeter square per mole. So these unit conversions and the related calculations are one of the prominent area from the chapter. So what is resistance? What is resistivity? What is conductance? Conductivity, molar conductance. I would insist you must also know what is equivalent conductance, lambda equivalent. Lambda equivalent conductance is equal to kappa into 1000 divided by normality. Kappa into 1000 divided by normality. Right? Are they same or different? Slightly different. If we are dealing with the HCl solution, we know molarity is equal to normality as n factor is 1. At the same time, if you are taking sulfuric acid where n factor is 2, I am sure you know molarity if it is x, normality will be 2x. So here it is molarity, here it is molarity x, the same thing here it will be 2x. That means lambda equivalent will be half of lambda m, or lambda m is equal to 2 times lambda equivalent. If it is coming x here, here it will be 2x. That means lambda equivalent is going to be half of lambda m. So you can write in this case lambda m is equal to 2 times lambda equivalent. Or you can have a generalization for any material. For any material, lambda m is equal to n into lambda equivalent, where n is n factor. Where n is n factor. For example, if we are dealing with the aluminum sulfate, for example, if we are dealing with the aluminum sulfate, what is the n factor for aluminum sulfate? Al2SO4 thrice. What is n factor? Aluminum sulfate. No idea. No idea. N factor is very simple. It is the total charge of cation or anion. Aluminum 3 plus into 2. It is 6. Sulfate 2 minus into 3. That is 6. This is n factor. Either the positive or negative value, which will be equal. So n factor equal to 6. For the case of aluminum sulfate, lambda m for aluminum sulfate, it is going to be 6 times lambda equivalent. Like that, you can also have a relation between molar conductance and equivalent conductance. Equivalent conductance, the unit will be Siemens centimeter square per equivalent. Siemens centimeter square per equivalent, or Siemens meter square per equivalent. That is the unit of lambda equivalent. Right? So that is about resistance, resistivity, conductance, conductivity, molar conductance, equivalent conductance, and its interrelationships. Right? Now on to a very important area, conductance versus concentration. Very, very important topic. Conductance versus concentration. Lambda versus concentration. Please understand, lambda versus concentration found to be different for different types of electrolytes. For strong electrolytes, the behavior is one way. For weak electrolytes, the behavior is other way. We can find the observation is to be like this: lambda m versus square root of concentration. We find for a strong electrolyte like a KCl, the graph is almost like this. For a strong electrolyte like KCl or any strong electrolyte, the graph is going to be like this. It is a straight line graph following the equation lambda m is equal to lambda m0 minus AC raised to half. Hope you understand clearly. C raised to half, that is root to c. It is coming along the x-axis. Lambda m coming along the y-axis. Y is equal to mx plus c. So this is the y-intercept. So when you extrapolate the graph, you are meeting at this point, that is lambda m0, called limiting molar conductance. This is called limiting molar conductance, or molar conductance at infinite dilution. Molar conductance at infinite dilution. Molar conductance at infinite dilution. That is limiting molar conductance, lambda naught, which comes as a y-intercept in this graph. What is the slope of the graph? What is the slope of the graph? Slope is equal to a constant A. Slope of the graph is equal to a constant A. So variation of lambda m versus root of concentration for a strong electrolytes makes a linear change. Slope of the graph is equal to a constant, which depends on nature of the electrolyte, and it depends on the temperature of the solution. It depends on temperature, it depends on nature of electrolyte. What is meant by nature of electrolyte? If you take KCl, if you take NaCl, if you take KBr, all are having, they are all 1,1 type electrolyte, A value will be fixed. For all this kind, it is 1,1 type electrolyte, A value is fixed. Suppose you are taking CaCl2, suppose you are taking MgBr2, it is 2 plus minus 1, it is 2,1 type electrolyte. For these, A value will be fixed for a particular type of electrolyte. 1 1 2 1 1 2 2 2 like that. For example, MgSO4 is a 2 2 type electrolyte. MgSO4 is a 2 2 type electrolyte. CaCO3 is a 2 2 type electrolyte. So for a particular type of electrolyte, A value remain fixed, and it depends on temperature also. And this formula very popular, known as Debye-Huckel-Onsager equation. Debye-Huckel-Onsager equation, that is meant for strong electrolyte. So the variation of molar conductance versus root of concentration, it is going to be a linear change for strong electrolyte. What about a weak electrolyte? For a weak electrolyte, it is not a linear change. It is going to be a curved one, and you can see the graph is moving like this. The graph is going like this for a weak electrolyte like acetic acid. Acetic acid is a weak electrolyte. It is a weak electrolyte. And see, number one, the value is low. Why the value is low? A strong electrolyte will undergo complete ionization. So the ions are maximum, the conductivity is maximum. For a weak electrolyte, the number of ions, alpha is less. Therefore, the number of ions will be less. So the molar conductance is less. Now, with the dilution, with the decrease in concentration, means with the dilution, the alpha increases. Alpha increases exponentially, and the number of ions increases, conductance increases. And the quite interesting point is that it is not a linear graph, it makes an exponential change. And the graph is moving almost parallel to y-axis. Means you cannot find out lambda naught value. Here we can find out lambda naught value. Here you cannot determine lambda naught value. So limiting molar conductance of infinite solution, infinite dilution, limiting molar conductance for a weak electrolyte, we cannot determine experimentally. And that is determined by mathematical manipulation using a law that is called Coloratius law. Using Coloratius law, mathematical manipulation is possible. That is what next coming. What is Coloratius law? Here one more point, important certain relationships you need to understand. That is for degree of dissociation. Degree of dissociation, alpha is equal to lambda m by lambda m naught. Try to incorporate this on the Ka value. Ka is equal to C alpha square minus by 1 minus alpha. So this you can incorporate here and try to find out some formula based questions. Equip yourself to answer some formula based questions. Degree of dissociation, alpha is equal to lambda m by lambda m naught. What is lambda m? Molar conductance at a given concentration. What is lambda m0? Limiting molar conductance, maximum molar conductance at infinite dilution or zero concentration. Infinite dilution means zero concentration. That's a theoretical idea. Okay. Now, how to find a lambda naught for weak electrolyte is done by Coloratius law. Coloratius law of independent migration of ions. Of independent migration of ions. Coloratius law of independent migration of ions, which states that the limiting molar conductance of electrolytes will be the sum of the limiting molar conductance of individual ions present. I repeat, the limiting molar conductance of electrolytes or molar conductance at infinite dilution of every electrolyte, it will be the sum of the limiting molar conductance offered by individual ions present in the solution. For example, lambda naught for HCl, it will be equal to lambda naught for H plus plus lambda naught for Cl minus. Lambda naught for NaOH. It will be equal to lambda naught for Na plus plus lambda naught for OH minus. Lambda naught for NaCl equal to lambda naught for Na plus plus lambda naught for Cl minus. Like this. Like this. Lambda naught for acetic acid. Lambda naught for acetic acid is equal to lambda naught for CH3COO minus plus lambda naught for H plus. Lambda naught for CH3COONA is equal to lambda naught for CH3COO minus plus lambda naught for Na plus. Like this. And lambda naught for CaCl2, it will be lambda naught for Ca2 plus plus 2 times lambda naught for Cl minus. Please be very careful. 2 times lambda naught for Cl minus. Lambda naught for A2B3. Lambda naught for A2B3. How comes? It is 2 times lambda naught for A plus 3 times lambda naught for B. That way it comes. That way it comes. This is what Coloratius law. What about lambda naught for AXBY? Lambda naught for AXBY. How comes? It is X times lambda naught for A plus Y times lambda naught for B. This is what the formula which is called Coloratius law. Using this we can find out lambda naught for weak electrolytes which otherwise cannot be determined. We can manipulate it. For example, among the following formulae, imagine you want to find out this you cannot determine using experimental technique. You cannot determine because it is a weak electrolyte. What is the problem? The graph is moving like this. The graph is moving like this. You see, the graph is moving like this. How can you determine lambda naught? You cannot. But you can determine, provided, imagine this data is available. This is a strong electrolyte. For a strong electrolyte, the data is available. For this electrolyte, suppose the data is available X. This is the strong electrolyte. Okay. For this electrolyte, suppose the data is available Y. This is a strong electrolyte. Okay. And now, for this electrolyte, the data is available Z. This is a strong electrolyte. So, this is a strong electrolyte, the data is available. This is a strong electrolyte, the data is available. This is a strong electrolyte, the data is available. You can find out what is this data. Very simple. How to determine? How to find out? Tell me. We want this. That means we want this and this. This you can get it from here. And this you can get it from here. So this is equation 1 and this is equation 2 and this is equation 3. Very simple. Equation 1 plus 2 minus 3 will satisfy the result. You add this and subtract with this. So what will be the result? What will be the result? Lambda naught CH3COO minus plus lambda naught Na plus lambda naught H plus lambda naught Cl minus. So this is equation 1, this one, and this is equation 2, that one, and now minus equation 3, minus lambda naught Na plus minus Cl minus lambda naught Cl minus. Now this much is X and this much is Y and this much is Z. So it is X plus Y minus Z. Now see what is the result. This and this will cancel. This and this will cancel. You are getting this plus this and that is equal to this. A simple mathematical manipulation using Colorash's law, we can determine the value of limiting molar conductance of weak electrolytes. That is the advantage of Colorash's law. Right? So the topics so far we were going through: galvanic cell, cell representation, standard electrode potential, electrochemical series, application, Nernst equation, various formulae related to Nernst equation, and resistance, resistivity, conductance, conductivity, molar conductance, equivalent conductance, variation of conductance versus concentration, Debye-Huckel-Onsager equation, strong electrolyte, and now weak electrolyte, and the application Colorash's law. Our next topic is Faraday's laws of electrolysis. Faraday's laws of electrolysis. Faraday's laws of electrolysis. We need to discuss first law, second law, Faraday's laws of electrolysis. That is the next topic. Next is Faraday's laws. First one, Faraday's first law. Faraday's first law. Faraday's first law, you might have heard about, which states that amount of chemical reaction is directly proportional to quantity of electricity passing through the electrolytes. Right? That is what the statement. Okay. Amount of chemical reaction, for example, we can say mass of substance deposited directly proportional to quantity of electricity passing through the cell. Okay. Amount of chemical reaction is a general comment used. It may be mass of material deposited, it may be mass of material dissolved, it may be a compound formed in the solution, it may be some metal extracted, right? So generally we use the terminology amount of chemical reaction is directly proportional to quantity of electricity passing through the solution. Okay. So M proportional to Q and M equal to a constant Z into Q. What is Z? What is Z? Z is called ECE. ECE. Electrochemical equivalent. Electrochemical equivalent, ECE, which depends on the material concerned. ECE for silver and copper will be different. For zinc it will be different, like that. How do we define ECE? What is the definition for ECE? Very simple. How do you define? M equal to Z when Q equal to 1 coulomb. So Z is defined as, ECE defined as mass of substance deposited or liberated or dissolved by the passage of 1 coulomb electricity. 1 coulomb electricity means, all of you know, Q is equal to I into T. So it is 1 ampere current passed for 1 second. That is 1 coulomb. So we can define Z as ECE, electrochemical equivalent, as the amount of matter deposited, amount of matter dissolved by the passage of 1 ampere current for 1 second. That is 1 coulomb electricity. That is the definition of ECE. Okay. And Z is equal to M by Q. So it will be kilogram per coulomb or gram per coulomb. That is the unit of Z, gram per coulomb. By the passage of 1 coulomb electricity, how much silver dissolved, how much silver deposited during an electrochemical process. That is called ECE of silver, like that. Okay. That is Faraday's first law. So we can write M equal to Z into I into T. M equal to Z into I into T. Okay. Now relating to Faraday's first law, you must know certain topics, which is nothing but 1 mole of any substance X. 1 mole of any substance X, it will require N Faraday. 1 mole of any substance X will require 1 Faraday. Suppose 1 mole a matter is dissolving during an electrochemical process. 1 mole of a metal is deposited. 1 mole of a compound is formed. 1 mole of a gas is liberated. Whatever it is, 1 mole of the material will require N Faraday. What is N? N is N factor. That is the number of electron transferred. Okay. Or we can say 1 equivalent of any matter will require 1 Faraday. 1 equivalent of any matter will require 1 Faraday. 1 Faraday means 1 mole electrons. 1 Faraday means 1 mole electrons that requires that will produce 1 equivalent of any material. So 1 equivalent of any matter needs 1 Faraday. 1 mole of any matter needs N Faraday, where N is N factor. Suppose we are talking about 1 mole reaction involving sodium. Sodium N factor is 1, so it requires 1 Faraday. What about calcium? If it is reacting 1 mole of every matter. Calcium N factor is 2, so it will require 2 Faraday. What about magnesium? Magnesium N factor is 2. It will require 2 Faraday. What about aluminium? Aluminium N factor is 3. It will require 3 Faraday. Already you have been taught. That is, N factor for elements means valency. Sodium monovalent, calcium divalent, magnesium divalent, aluminium trivalent, so on. What about 1 mole hydrogen? 1 mole hydrogen. 1 hydrogen is 1 equivalent. H2 means 2 equivalent. So it is N factor 2. It is requiring 2 Faraday. What about 1 mole oxygen? 1 mole oxygen. 1 oxygen, 2 minus. So 1 oxygen, it is divalent. 2 oxygen means it is valency factor 4. So it will be 4 Faraday, like that. What about 1 mole chlorine gas? Again, 2 Faraday. Okay. 1 mole water reacting in a electrochemical process. 1 mole water, very simple. You can see either positive part or negative part. So it is H plus, 2 numbers. So it will be 2 Faraday. What about 1 mole Al2O3 reacting? 1 mole aluminium oxide reacting. What is N factor? What is N factor? Exactly. It will be aluminium 3 plus into 2. It is 6 plus. Oxygen minus 2 into 3 minus 6. This is the N factor. So it is 6. It requires 6 Faraday. Like that. So 1 mole of any matter that is reacting, we can have the talk on how much Faraday is required, based on which definite sort of numerical problems we are going to encounter in most of the board exams as well as entrance examination, and we are going to do those problems in the classes. Very important point. Okay. Next is Faraday's second law. Next is Faraday's second law. Faraday's second law. What is the statement for Faraday's second law? Faraday's second law states that the amount of matter deposited in 2 different electrochemical cells will be directly proportional to their equivalent mass, provided same quantity of electricity passing through the solution. When same quantity of electricity passing through the electrochemical cells, the amount of matter deposited or dissolved, amount of matter reacting in each cell, it will be directly proportional to their equivalent mass. That is what Faraday's second law. So it comments that W proportional to E. W is the mass of substance dissolved, deposited or produced in the solution during an electrochemical process. It is directly proportional to the equivalent mass of the material provided the current amount of electricity passing through remain the same. For example, suppose you have a cell which is cell 1, this is cell 1. Imagine there are two electrodes connected and this cell is parallelly connected to another cell. I'm sure you know the importance of parallel connection. The amount of electricity passing through will be same. So this is cell 1, this is cell 2. Imagine in cell 1 we are producing magnesium. Imagine in cell 2 we are producing aluminum. So this is a cell which electrolytic preparation of magnesium is involved. And the second cell we are producing aluminum and they are connected in parallel condition. And you know what is series connection. It is connected with a series connectivity. You know the importance of series connectivity. Series connectivity means the amount of electricity passing through will be same. So cell 1 series connection with the cell 2. Therefore, the quantity of electricity passing through, if it is Q here, the same will be passing through here Q. So amount of electricity passing through the solution remain the same. Now we can apply Faraday's law. Faraday's law states that when the same quantity of electricity passing through two electrochemical cells, the amount of material deposited will be directly proportional to their equivalent mass. So in the two conditions you can write W1 by W2 is equal to E1 by E2. As you know, it is W proportional to E. So W1 by W2 is equal to E1 by E2. For example, mass of magnesium deposited by mass of aluminum deposited will be equal to equivalent mass of magnesium divided by equivalent mass of aluminum. What is equivalent mass of magnesium? It is molar mass by valency. Molar mass by valency. So what is molar mass? Molar mass of magnesium 24 divided by valency 2, it will be 12 grams. While in case of aluminum, the molar mass is 27 divided by valency 3, it will be 9. So weight of magnesium divided by weight of aluminum is equal to 12 by 9, that is 4 by 3. It will be in the ratio 4 by 3 ratio. So if you are getting 4 gram magnesium deposited, a simultaneous deposition of aluminum will be 3 gram. That's how the reaction happens, or that's how the law, Faraday's law, has been illustrated. Faraday's second law. Is it clear? So Faraday's first law, Faraday's second law. Faraday's second law talk about the amount of material deposited in two different cells which are connected in series so that the amount of electricity passing through the solution remain the same. Then the matter deposited will be directly proportional to their equivalent mass. It was already taught what is equivalent mass. Equivalent mass will be molar mass by n factor. What is n factor for elements? Valency. It was taught. So that is Faraday's second law. Is it clear? Is it clear? So Faraday's first law and Faraday's second law. Next is products of electrolysis. Next is products of electrolysis. Products of electrolysis. In products of electrolysis, we need to maximum go through the examples. Different electrolytes when taken for the electrolytic operation. What will be the different materials obtained according to electrochemical procedures, that we need to go through as many examples as possible. Products of electrolysis depends on various factors. Products of electrolysis depends on various factors. Number one, what is the electrolyte you take? What is the nature of electrolyte you take? For example, NaCl, molten state or aqueous solution. Different will give different products. So whether the electrolyte taken in molten state or in aqueous solution, product will be different. Whether you take a inert electrode like platinum or whether you take a active electrode, interacting electrode, reacting electrode, the product will be different. Current intensity will difference the product. Current intensity will influence the product obtained. So different factors are there which influences the products obtained in electrolysis. Nature of the electrolyte, the way you take, nature of the electrodes that you take, current intensity, etc. all can influence the products obtained. For example, let us discuss first case, molten NaCl. Suppose we take molten NaCl. NaCl in the molten state I am taking with the inert electrodes. What will be the product obtained? Very simple to understand. If you are taking molten NaCl using non-reacting electrodes, there are very simple procedure. We have Na plus cation which will move towards cathode, and we have Cl minus anion which will move towards anode. At a cathode, there will be reduction taking place, and what happens? Na plus electron converted to Na. So you get metallic sodium produced at a cathode by reduction process. What about at anode? At anode, Cl minus proceeding to anode, and there will be oxidation process, and you can find 2 Cl minus converted to Cl2 gas, liberating 2 electrons. So at the cathode, there is reduction, you get metallic sodium. At anode, you get oxidation, chlorine gas is liberated. Okay. Suppose at the same time, we are taking aqueous NaCl. Suppose if you take aqueous NaCl, product will be different. Why the product is different? We have Na plus, and since it is aqueous medium, we have H plus. We have Cl minus, and since it is aqueous medium, we have OH minus. So there are 2 cations and 2 anions. So there will be a competition, which will be reduced, which will be oxidized. Right? At a cathode, the reduction depends on the reduction potential. This is having a negative reduction potential, that is lower reduction potential, and this is assigned to be 0. So this is having a greater reduction potential. So hydrogen gas will be liberated at a cathode by reduction process. Meanwhile, at the anode, what's going to happen? There is a competition between Cl minus and OH minus. Theoretically speaking, the discharge potential of OH minus is lower, and actually it should be OH minus oxidized and we should get oxygen gas. But practically, the bubbling of oxygen gas, the production of oxygen gas requires some extra potential, which we call it as over potential or bubbling voltage. So due to that over potential, it is not oxygen gas obtained at anode, we get chlorine gas obtained at the anode. So chlorine will be liberating, and you will get chlorine gas produced at the anode by oxidation. Right? And what remain in the solution? In the solution, NaOH remain. So what is the nature of the solution? Solution turn more and more alkaline. What happened to the pH of the solution? pH drops or increases? pH will increase as it is becoming more and more alkaline in nature. Is that clear? Let us go to another example. Suppose we are taking copper sulfate solution electrolyzed. Copper sulfate solution taken for electrolyze. With the inert electrode, using platinum electrode, copper sulfate solution is electrolyzed. What will be happening? We have again aqueous solution. You have Cu2 plus and H plus, which is interacting at the cathode, and we have SO4 2 minus and OH minus at the anode, because it is a aqueous solution taken. But it is a non-reactive electrode. As I told, we are taking platinum electrode, say for example. Now once again, what is happening at the cathode? Is it copper deposited or hydrogen gas liberated? Earlier we have seen sodium and H plus, hydrogen gas is liberated because sodium has got a negative reduction potential, lower reduction potential. Coming to copper and H plus, copper has got a positive reduction potential plus 0.34 volt. So this has got a greater reduction potential and hence copper will be deposited at the cathode by reduction process. Unlike the previous story, here not hydrogen gas is liberated, rather copper metal is deposited. Clear? Because copper is having a positive reduction potential and hydrogen assigned to be 0 value. Hope it is clear. What is happening at the anode? At the anode, once again, we have sulfate and OH minus. Once again, OH minus has got a lower discharge potential, much lower compared to sulfate. No point of any competition. It is oxygen gas liberated at the anode. OH minus will undergo oxidation at anode and oxygen gas will be released at the anode. This is what the story when you take aqueous copper sulfate is electrolyzed using platinum electrode. What if it is a reacting electrode? Copper sulfate electrolyzed using copper electrode. Aqueous copper sulfate solution electrolyzed using copper electrode. The story will be entirely different. Why? Because it is a reacting electrode. So what is the story now? It's very simple. Known to all, we are taking copper sulfate solution and we are taking an anode which is a copper electrode. This is anode, and we are taking a copper sheet as cathode and they are connected externally and we are passing electricity. At anode, there will be oxidation taking place, nothing but copper atoms will be dissolving into the solution. So copper solid is oxidized to Cu2 plus 2 electron, and Cu2 plus will be coming to the solution, undergoing oxidation. So copper metal from the anode will be dissolving in the solution. Meanwhile, what is happening at a cathode? At a cathode, we can see Cu2 plus from the solution is depositing over cathode by reduction. That is Cu2 plus 2 electron. You are getting Cu solid. So at anode, copper dissolves. At a cathode, copper deposits. So there is a dissolution, decay at anode, and there is a growth at a cathode. So over the course of time, anode undergoes a decay, and over the course of time, cathode undergo a growth. Right? And all impurities present in this metal will be sedimenting over here. You are remembering, I believe it is called anode mud. Anode mud. Anode mud is not simply impurity, it contains valuable metals like copper is always contaminated with atoms of gold, platinum, antimony, tellurium, etc. Costly, precious metal atoms we can get from the anode mud. Right? And they will be settled over the vessel, at the bottom of the vessel. Anode mud it is called. Right? So it is a electrolytic refining technique used for refining of impure sample of metal. Now the story is entirely different. At anode, copper is dissolving. At a cathode, copper is depositing. So it is a reacting electrode. So inert electrode, reacting electrode, scene will be different. Story will be different. Molten electrolyte, aqueous electrolyte, story will be different. Current intensity can influence the products obtained. So various factors influences the products of electrolysis, which you need to go through as many examples as possible, for particularly the examples in the NCERT textbook. Right? That is about products of electrolysis. Now we are switching on to the last portion of the chapter. What is the last portion of the chapter? It is talking about commercial cells. Commercial cells, we call it as batteries. Batteries. A talk on batteries. Batteries are nothing but electrochemical cells which produces spontaneous energy released from the chemical energy stored in the system into electrical energy and used for useful purposes running so many equipments, systems and all. That is commercial battery. Battery, all of you know, there are two varieties. One we call it as primary cells, use and throw. Next is called secondary cell, which we can recharge and use again. There are two varieties of cells, primary cell and secondary cell. Whatever primary or secondary cell you learn, what is the main points to be concentrated? Whenever you learn about a cell, what are the main points to be concentrated? You have to look at what is the material used as anode. What is the material used as cathode? What is the material used as electrolyte? Electrolyte. What is the anode reaction? Anode reaction. What is the cathode reaction? And what is the net reaction? And if there are any specific uses commented, that we need to go through. Each cell when you learn, like a dry cell, lead storage battery, nickel cadmium cell, various types of cell when you go through, these are the particular points you must review and study, repeatedly go through, because that is going to be the question. What is the material used as anode, cathode, electrolyte, anode reaction, cathode reaction, net reaction, specific uses or specific comments regarding a particular cell given. Let's go through one by one. First of all, dry cell it is. We are going to discuss about a primary cell. Primary cell is the one which we can use and throw, that is a primary cell. For example, dry cell. This is a talk on dry cell. A diagram is available. This is dry cell. Laclantius cell. A primary cell given, and this is a dry cell. The diagram is available. Okay. So what is used as anode? Anode, it is zinc container that act as anode. So zinc container act as anode. And carbon, cathode is carbon, graphite, that is cathode, which is surrounded by powdered manganese dioxide and carbon. So that is about electrodes. Zinc is working as anode and carbon, graphite is working as cathode and is surrounded by powdered manganese dioxide and carbon. Then what is electrolyte? Electrolyte is a moist paste of ammonium chloride and zinc chloride is used as electrolyte. So what is anode? What is cathode? What is electrolyte? Okay. Now what is anode reaction? Anode, always there is oxidation. So zinc undergo oxidation. That is what happening anode. Zinc is converted to zinc 2 plus. What is happening at the cathode? At the cathode, MnO2, that is manganese dioxide, is undergoing reduction. MnO2 in ammoniacal medium, it is converted to MnOOH. What is the oxidation state of MnOOH? How it is undergoing reduction procedure? At a cathode there will be reduction. So manganese, it is +4 state converted to MnOOH. OH is -1, oxygen is -2, so manganese is +3. So manganese +4 is converted to +3 state. At a cathode there is reduction, at anode there is oxidation process. When you add both, you get a net cell, and the net potential obtained will be 1.5 volt. That is the potential given, and it is going to be a dropping potential. It is not going to be a continuous fixed potential, as it involves ions. There is zinc ammonium complex is involved, and ionic concentration when changes, there will be change in EMF. So EMF is not a constant EMF, it is a varying EMF. That is about a primary cell. So zinc work as anode, graphite work as cathode, electrolyte will be a paste of ammonium chloride and zinc chloride. At anode reaction, cathode reaction, and the characteristics. And next one, it is another primary cell which is mercury cell. Next one, it is a mercury cell. So in mercury cell, what are the electrodes involved? What are the characteristics in mercury cell? Let's have a look at. It is zinc mercury amalgam working as anode. Zinc mercury amalgam working as anode, and a paste of mercury oxide and carbon work as cathode. So anode will be zinc mercury amalgam. Cathode is a paste of mercuric oxide and carbon. And what is electrolyte? Electrolyte is a paste of KOH and zinc oxide. And this is anode reaction where there is oxidation. Zinc 0 is converted to zinc oxide +2 state, oxidation. At a cathode, it is reduction. Mercuric oxide +2 state converted to mercury 0. So at anode, there is oxidation. At a cathode, there is reduction. And the speciality of mercury cell is that it is going to give you a constant EMF as there is no ions involved in the reaction, right? And hence it is applied in most of the electronic devices and all. Mercury cell, all of you know this is mercury cell and is going to give you a constant potential. This is the overall reaction for the mercury cell. Okay. Now it is about lead storage battery. It is about lead storage battery, lead accumulator, lead storage battery. All of you know this is the lead storage battery which is used in automobile systems, automobile vehicles, along with the what do you call inverters and all at home. Everywhere it is used as a lead storage battery, lead accumulator. This is a lead accumulator. And what are the features involved in lead accumulator? Let's have a look at. See that what is used as anode. It is consisting of a lead anode, lead used as anode, and a grid of lead packed with lead dioxide is acting as cathode. So lead work as anode, a grid of lead packed with lead dioxide act as cathode. A 38% solution sulfuric acid used as electrolyte. Right? So in every cell when you learn, these are the points to be noted down. And see the anode reaction. At anode reaction, lead is oxidized to lead sulfate. Lead is oxidized to lead sulfate. At a cathode reaction, what happens? Lead oxide is reduced to lead sulfate. So here Pb oxidized to PbSO4, while here PbO2 reduced to PbSO4, and this is the overall reaction. That is the overall reaction. Pb plus PbO2, you get PbSO4. Pb plus PbO2, you get PbSO4. And see that Pb0 is converted to +2 state, and Pb plus 4 is converted to +2 state. So Pb0 coming to +2 state, Pb plus 4 coming to +2 state, two different oxidation state of an element. Two different oxidation state of an element coming to a common state. This is something opposite to disproportionation type reaction, and it is called comproportionation. Comproportionation, or called synproportionation. Comproportionation, or called synproportionation. An element in two different states coming to a common state by a redox reaction. That is called just something opposite to disproportionation type reaction. Okay, so these reactions are involved in the discharging of lead storage battery. Lead storage battery, all of you know, it is a secondary cell. It is a secondary cell. It can be recharged and used again. So how the recharging process is done? Discharging means by this operation we are getting energy from the cell. Now recharging means we are giving energy to the system. Entire operation will reverse. Here the reaction will be opposite. Here the reaction will be opposite. Overall reaction will be opposite. In overall reaction, 1 mole Pb, 1 mole PbO2, 2 mole sulfuric acid consumed. You get 2 mole PbSO4 and 2 mole water. When it reverse, it go to the other side. 2 PbSO4 plus 2H2O, you get the reverse reaction happening during recharging process. So please be very careful when you attempt for the exam questions. Whether they are asking anode reaction, cathode reaction, net reaction for discharging process or recharging process, which will be mutually opposite. Is it clear? That's about a secondary cell lead storage battery. So primary cell, dry cell, mercury cell. Now it is lead storage battery. There is another one, nickel cadmium cell. That is also a secondary cell. Nickel cadmium cell. This is the overall reaction of nickel cadmium cell, and this is the diagrammatic representation of nickel cadmium cell, where cadmium 0 is oxidized to +2 state and that act as anode, while nickel hydroxide, which is +3 state, reduced to nickel hydroxide +2 state, that is working as cathode. So cadmium undergo oxidation, working as anode. Nickel hydroxide undergo reduction, working as cathode. Is that clear? That is about nickel cadmium cell. One of the most important category is fuel cell. There is a category fuel cell. What are fuel cells? Fuel cells, which are galvanic cells basically, that are designed to convert the energy of combustion of fuels like hydrogen, methane, methanol, etc. directly into electrical energy. That is called a fuel cell. So the combustion reaction of a fuel is converted to electrical energy. That is the purpose of a fuel cell. Now here we are going to discuss a simple fuel cell, hydrogen oxygen fuel cell. This is H2O2 fuel cell. There you can find 3 compartments shown in the diagram. There is a left compartment working as anode, where hydrogen gas is pumped. There is a right compartment working as cathode, where oxygen gas is pumped. Both are made up of carbon. Both are made up of graphite. Right? The electrodes are made up of graphite. You see that the porous carbon electrodes, we are using porous carbon electrode, and the electrolyte used is aqueous sodium hydroxide solution. Concentrated aqueous sodium hydroxide solution used as electrolyte. So this is porous carbon electrode. And here we have the central compartment where there is electrolyte available, concentrated aqueous NaOH solution. You see what is happening in the left compartment. Hydrogen gas will be migrating to the central compartment, and it is undergoing oxidation. H2 gas undergo oxidation converted to H2O. While in the right compartment, oxygen slowly diffuses into the central compartment. At the cathode, oxygen is reduced to OH minus. So when you add cathode anode reaction, the net reaction is very simple, formation of water. H2 plus O2 giving H2O. So this 2H2O, 2H2O will cancel, 4OH minus, 4OH minus will cancel. You get H2, 2H2 plus O2 giving 2H2O. That is the net reaction. And I don't have to tell you, unlike the conventional resources of energy, fuel cells are like this. Fuel cells are absolutely pollution-free systems, and efficiency is very high. When you compare the thermal power plants, which is giving efficiency in the range of 40-50%, here the efficiency is 70-80%. But how to handle this system is somewhat costly and difficult. And if that is possible, it's going to be a high degree of hydrogen economy in the case of energy utilization, and the cells which are highly useful as a resource of energy for various functioning systems, including automobile vehicles. That is about fuel cell, hydrogen oxygen fuel cell. And the final topic is on corrosion. a topic called corrosion. What is corrosion? A slow degradation of a metal is called corrosion. A slow degradation by electrochemical processes, environmental processes, where metal is oxidized to metal oxide. That is what called corrosion. A corrosion, simple corrosion is rusting of iron. Rusting of iron is explained as a mechanism of corrosion. Right? Here you can find some irregular surfaces on metal. Irregular surfaces on iron metal where some moisture content is settled. It acts as a micro electrochemical cell. And there actually the rusting triggers some irregular surfaces where moisture is involved. It acts as a tiny cell. And you see, this area will be acting as a anode. This area will be acting as a anode, and this area will be acting as a cathode. At anode, there is oxidation taking place, and iron is converted to Fe2 plus. And these electrons are carried away to the other side where it is interacting with oxygen. Oxygen and H plus, it is converted to water. Subsequently, Fe2 plus will be converted to Fe3 plus, and finally with oxygen, it is converted to rust. This is rust, Fe2O3, that is called rust, ferric oxide. Hydrated ferric oxide is called rust. And the reaction happening, oxidation at anode region, iron is converted to iron 2 plus. At the cathode region, oxygen is converted to H2O, and overall reaction, Fe2 plus with H2O with oxygen, you get Fe2O3, that is rust. This is anode reaction where the potential you can find negative 0.44 volt. It will act as anode. It will act as anode. At a cathode, the reaction will be this one, and you can very well understand how acid medium support the rusting process. Acid medium can promote the rusting operation, while anti-rust solutions used are alkaline solutions. So H plus medium can promote the rusting operation. As you can see, this is the overall reaction, Fe plus O2 plus 4H plus. So acid medium promote the rusting process. We get Fe2 plus with H2O. That is the overall reaction potential EMF. You can find it is positive. E cell positive means it is a spontaneous process. Rusting is a spontaneous process, slow process where iron is irreversibly converted to rust, hydrated form of iron oxide. This is rust, Fe2O3 XH2O. And various way to prevent corrosion. Prevention of corrosion is also very important topic which learned from the lower classes itself. Various methods used for preventing the corrosion. Number one, painting. The surface is painted, or some chemicals, bisphenol, a chemical used for preventing corrosion, bisphenol, some anti-rust solutions, or coating with some active metals, zinc, tin, etc. Zinc, coating with the zinc, all of you know, galvanization, galvanized iron, GI, galvanized iron. Galvanization means coating with the zinc. That are inert, some other electrochemical methods are sacrificial electrodes. Hope you have heard about. Magnesium blocks are used in the bed sheath of ships, in ships and all. The bottom portion of the bed, it is fed with a sheath of magnesium blocks. It is to prevent the corrosion action. Or when huge iron pipes are buried into the ground, at a regular interval of period of time, we can see the iron blocks is connected with the magnesium blocks. The iron pipes are connected with the magnesium blocks. Imagine huge iron pipes are buried into ground, into the earth. Huge iron pipes. It cannot be galvanized. So this is the pipes inside the earth. What we do is, this is connected with the magnesium block. Now, what is the advantage? This is iron and this is magnesium. This is an active metal which will work as anode, and this will be protected as cathode. And the magnesium will be at anode, there will be decay. Decay is happening, corrosion is happening, destruction is happening at anode. So magnesium will undergo decay and it will protect the iron pipe. Sacrificial protection. These are various methods of preventing corrosion. With that, the chapter is getting concluded. Let me review. Let me just recap. We started from galvanic cell, construction of galvanic cell, cell representation, cell reaction, standard reduction potential, applications of electrochemical series, Nernst equation, various formulae connecting Nernst equation, then resistance, resistivity, conductance, conductivity, molar conductance, equivalent conductance, various formulae connected, then variation of molar conductance versus concentration, strong electrolyte, weak electrolyte, Debye-Huckel formula, Colorash's law and its application. Then electrolysis, Faraday's laws of electrolysis, first law, second law and its applications, products of electrolysis, and finally commercial cells batteries. With that, we conclude the chapter, a very important chapter from the 12th standard topic, electrochemistry. With another chapter, we will meet again in another class. Okay, till then, bye. See you.